The second part of Chapter 7 continues on to talk about other periodic properties. One of the periodic properties that we're going to be looking at is electron affinity. I know you already know what electronegativity is, which is the desire to gain electrons. But electron affinity is a little bit different, but it's also quite similar. You can see here it's the energy change accompanying the addition of an electron to a gaseous atom. So for example, in this example you can see it's chlorine plus an electron produces the chlorine ion, and how much energy is released as a result of that particular change. The trends in electron affinity are shown in this particular diagram, and they're showing the s and the p orbitals. In general, electron affinity becomes more exothermic as you go from left to right across a row. Now you notice that the halogens are some of the highest on the table. You can also see that the noble gases are approximately 0 or greater than 0. That means that they tend to be endothermic. It's very difficult to add an electron to those because of course they have a stable octet. There are, however, some discrepancies between a continuous decrease in energy or continued exothermic reactions. And you can see the two areas circled on this particular slide. Why is it the way it is? Well, the one trend we see is the first problem comes between groups 1A and group 2A. You can see when lithium loses or an electron is added to the lithium atom, it releases 60 kilojoules of energy, whereas beryllium, although it's to the right, it actually is a bit endothermic. And that's because, remember, beryllium has a filled s sublevel, and when we add an additional electron, it has to go into the p orbital, which is a problem. And I will attempt to show that using the ink, if it will allow me to do that. Sometimes, you know, I have difficulties with these PowerPoints doing what I like them to do. Let's see, can I get the ink color to show up? Come on, ink color. Oh dear. Alright, well, I'll just show there's beryllium. And if we were going to add another electron, it would be adding it to the p sublevel, or p orbital, and therefore perhaps be less exothermic. The electron is farther from the nucleus and feels repulsions from the s electrons, as it says here. The second problem or discrepancy comes between groups 4A and 5A. And again, this would be between the carbon family and the nitrogen family. Now, why would that be the case? Well, of course, when you have carbon, you have 2 electrons in the p sublevel. And to add an extra electron would mean that the sublevel is half full. However, with nitrogen, it is already half full, and it would be somewhat resistant to have an extra electron added to that, because then you would have to start pairing up the arrows in the sublevel, and the electron-electron repulsions would be relatively high because you're trying to put 2 electrons in the same orbital, which of course can happen, but in terms of energy released when this happens, you can see for nitrogen in this case it's greater than 0. And according to this PowerPoint, group 5A has no empty suborbitals, or empty orbitals, and the extra electron must go into an already occupied orbital, creating repulsion. In general, you know, the periodic table is divided broadly into 2 parts, metals and nonmetals. Metalloids, of course, are those that elements that kind of sit along the staircase. Hydrogen is a nonmetal, as are the elements over here on the right side of the staircase. Majority of the periodic table is made up of metals. Francium is the best metal on the periodic table because it personifies all the characteristics of a metal. Metals lose electrons easily, they have a large radius, low ionization energy, low electronegativity, and low electron affinity. On the other end of the spectrum, of course, excluding the noble gases because they rarely form compounds, fluorine is the best nonmetal. And again, it is the best nonmetal because it does what nonmetals do best, which is to gain electrons. It's a very small atom, gains electrons easily. It has a very high electron affinity and a very high electronegativity. And just some quick properties of metals and nonmetals. You probably already know this particular set of information, so we really don't need to dwell on it very much. The remains of this PowerPoint just talk a little bit about metals and nonmetals, so I'm not really going to go over it in much detail. But you can see it says metals tend to form cations and nonmetals tend to form anions, as shown here, and you can see some of the various oxidation states of some of these metals. Metals also tend to have a luster. They are malleable and ductile, and they conduct heat and electricity. And of course, as we've said earlier, compounds formed between metals and nonmetals tend to be ionic, and metal oxides tend to be basic. Nonmetals, however, are dull, brittle, and poor conductors of heat and electricity. These gain electrons in reactions with metals to acquire a noble gas configuration. And substances containing only nonmetals are molecular compounds. Sometimes we talked about that as being covalent bonding, but it's called a molecular compound as well. And most nonmetal oxides are acidic. Metalloids have characteristics of metals and nonmetals, depending, of course, on which one we're looking at. For instance, silicon looks shiny, but is brittle and fairly poor conductor of electric current. So, those are metalloids. I'm going to skip this last section of the PowerPoint from the textbook on group trends because it just goes through every single family of the periodic table. Just talks about some generalities, but I don't think you really need to know this information in this detail. So we're going to stop this particular discussion of periodicity right here. And so between this discussion and the previous one, you have all the information you need to know about periodic properties, or at least most of the information.